Okay, so we're continuing on with chapter 6. We're still talking about normal probability distributions. In 6.6, we're going to talk about normality as an approximation for a binomial distribution. We have covered binomial distributions previously in chapter 5, section 2. So for a full refresher on that, you can go back to 5.2. Some key concepts in 6.6. In this section, we present a method for using a normal distribution as an approximation to a binomial probability distribution. Now, definitely go back to 5.2 if you need more of a refresher on these notations, but given probabilities P and Q, remember for successes and failures, and for binomial distributions, we can have only either a success or a failure. It can only be either one of those two categories. So because that's true, then P and Q need to add up to 1. So to find Q, then if we know P, we can take Q is equal to 1 minus P. Or if we know Q, but we don't know P, we could take 1 minus Q is equal to P. So it's Q plus P is always equal to 1. They're complements of each other. And again, we have a sample size of lowercase n. Then if these conditions of n times P is greater than or equal to 5, and n times Q is greater than or equal to 5, if both of those are satisfied, then the probabilities from a binomial probability distribution can be approximated reasonably well using a normal distribution having these parameters. So in order to find the population mean, we'll take n times P. In order to find the population standard deviation, or sigma, we'll take the square root of n times P times Q. Going back up here quickly to these bullet points, again, I definitely recommend going back to chapter 5, section 2. There you'll see more about this notation where lowercase p is the probability of success in one of the n trials, and lowercase q is the probability of failure in one of the n trials. Okay, so we have to determine, are these requirements satisfied? Take the number of trials n times the probability of success in one of those trials n, so that's p. Take n times p, see if that's greater than or equal to 5. Then we also need to check this requirement, the number of trials n times q, where q is the probability of failure in one of the n trials. If n times q is greater than or equal to 5, so both of these requirements have to be true, then we can approximate a binomial probability distribution using a normal distribution. So again, if these requirements are satisfied, then we go down to this bullet point and we approximate the population mean and the standard deviation by these equations. Another key concept in 6.6 we'll go over is when we approximate a binomial probability distribution using a normal distribution, there's one main caveat we need to keep in mind. So that caveat is that a binomial probability distribution is discrete. When data is discrete, we have whole numbers for the random variable of x. But if we approximate a binomial probability distribution as a normal distribution, well, a normal distribution is continuous. So we need to compensate for this difference if we are going to take data from a binomial probability distribution and use approximations of a normal distribution. So in order to compensate for this, we use what's known as a continuity correction. So we have a whole number x, which we'll do an example of, represented by the interval from x minus 0.5 to x plus 0.5. We will talk a lot more about this continuity correction today in this lecture. To refresh you visually on discrete versus continuous variables, here's examples of discrete, here's examples of continuous, where a discrete random variable has a collection of values that is finite or countable. So you can see here we have these individual data points where we can count each of those data points. Whereas for a continuous random variable, it has infinitely many values and the collection of values is not countable. So for example, for time, we can have every single time point in between 1 second and 2 minutes, for example. So each of those time points is continuous and we can't actually count each of those individual data points. So again, for binomial probability distributions, these are discrete, whereas for normal approximations, it's considered continuous. So because we're taking a discrete distribution and we're approximating it as a continuous distribution, we need to use this continuity correction, and I'll show you how to do that today. Before we go into more on 6.6, I do want to give you a quick review on binomial probability distributions in addition to the notation that you saw. So binomial probability distributions, they have a fixed number of trials, or lowercase n. The trials are independent from one another. So one trial could occur, it doesn't affect the outcome of that other trial. Number 3, trials are each classified into 2 categories. That's where that word binomial comes from. Those 2 categories are known as a success or a failure. So our outcomes can only be either a success or a failure. It's only one of 2 options, so that's why we have a binomial distribution. And then lastly, trials with the property that the probability of success remains constant. So again, we have some probability of success in one trial. That probability of success 100 trials later is not changed. It remains the same. Here's more of this notation. We saw a little bit already in this section. So n is the number of fixed trials. X or S is the number of specific successes amongst n trials. It can be called either X or S, so keep that in mind. We've seen that before in 5.2. Lowercase p, again, is the probability of success in one of those n trials. Lowercase q, the probability of failure in one of those n trials. And we can find q if we don't know it by taking 1 minus the probability of success, or lowercase p, in one of the n trials. Because again, q and p are complements of each other, the data points can only be either a success or a failure. They have to fit into one of those 2 categories. Now, you may be wondering, why do we keep approximating data as a normal distribution? Why do we need to do that? Why can't we just treat the distribution as it is if it's not a normal distribution? Well, to answer that, data is easier to deal with when we have normal distributions. We know how to deal with normal distributions using either Excel or Table A2, and it really just simplifies how we can process that data. So in 6.3, for example, we saw that the sampling distribution of sample proportions tends to approximate to a normal distribution. Recall from 6.3, if we had a population and we separated that population into all the different various samples, then from each of those different samples, we could get a proportion value, we could get a mean value, we could get a variance value. Those 3 categories were all considered unbiased estimators. When we then took the mean of all the proportion values from each of those samples, then we got the proportion value that represented the population. Similarly, for means and variances as well, we could take the mean of all of those samples, then take the mean of all of the sample means to get the population mean. For variances, we could take the variance of each of those samples, then take the mean of all the sample variances to then get the population variance. If you remember from 6.3, when we took sample proportions or sample means and took the mean of all of those, then those data points did approximate to a normal distribution. Go back to 6.6 and or ask me any questions you have if you need help with 6.6. 6.6 was definitely one of the trickier sections in chapter 6, so definitely go back and practice that and make sure you're comfortable with that material. So now coming back to 6.6 specifically, in this following probability histogram for a binomial distribution where we have n number of trials is 580, lowercase p is 0.25. Remember, lowercase p is the probability of success in one of these n trials. Here's what that histogram looks like. We have probability on the y-axis, and we have number of yellow P's among 580 different trials. The scientist that worked on data like this is from the biology world, so this is Mendel. So in one of Mendel's famous hybridization experiments, he expected 25% of his 580 P's to be yellow. Again, we have 580 P's, we have 580 trials. We're calling those P's being yellow our measure of success. Therefore, we represent lowercase p, or the probability of getting a yellow P among one of the N trials as 25%, or taking that out of a percentage, it's 0.25. We take 25% divided by 100, that's 0.25. 0.25 is our probability of getting a yellow P. Because that's our chosen measure of success, then lowercase p is 0.25. Let's keep going now. So let's say he actually got 152 yellow peas with a rate of 26.2% now. So this is what he expected to get. 25% of all of the 580 peas were going to be yellow. What he actually got is, though, amongst those 580 trials, he got 152 yellow peas. That equates to a success rate of 26.2. How would you calculate that? Well, you'd take 152 divided by 580, multiplied by 100 to get 26.2%. Looking at this histogram then, the probability versus the number of yellow peas among 580, remember this is our binomial distribution because we can either have success or failure, where success is represented by getting a yellow pea and failure is getting some other color aside from yellow. So here's our binomial distribution. Because it's bell-shaped, this does suggest to us that we can use a normal distribution to approximate the binomial distribution of data that we're working with. So if you remember how we assess normality, one of the ways we can do so is just visual inspection. Does this appear to be a bell-shaped symmetric curve? That would imply to us that we can use a normal distribution to approximate this data. Other than just visual inspection, though, we need to go through these requirements to determine if we can use a normal distribution as an approximation to the binomial distribution. Let's talk through those requirements now. So number one, the sample is a simple random sample of size n from a population in which the proportion of successes is p. Or the sample is the result of conducting n independent trials of a binomial experiment in which the probability of success is lowercase p. So again, we're going through the requirements to determine if we can use a normal distribution as an approximation to a binomial distribution. So requirement number 2 is that n times p is greater than or equal to 5, and n times q is greater than or equal to 5. Both of these have to be true as requirement number 2. So those are our 2 requirements. If both of those are satisfied, then to approximate our data as a normal distribution, the probability distribution of the random variable x can be approximated by a normal distribution with these parameters. Those parameters are such that mu, or the population mean, is equal to n times p, and sigma, the population standard deviation, is equivalent to the square root of n times p times q. What are each of these notations again? Right, so mu is the population mean, sigma is the population standard deviation, n, p, and q we've talked about a few times now, so go back and look at previous slides if you need to make sure you know what n, p, and q are. Now, as one of the key concepts in 6.6, I talked about this continuity correction idea. So again, for this correction, when using a normal approximation, we need to adjust the discrete whole number x by using a continuity correction. This is so that any individual value of x is represented in the normal distribution by a certain interval. That interval is from x minus 0.5 to x plus 0.5. This is because, again, the binomial probability distribution is discrete while a normal distribution is continuous. So we need to correct for that when we're making this approximation. To correct for this normal approximation, instead of just looking at the value of x, we're going to look at the value from x minus 0.5 to the value of x plus 0.5. We'll talk a lot more about this. Okay, so now we've touched on the requirements, we've talked about how we would execute this continuity correction, and we'll practice doing that. Now let's talk through the procedure for using a normal distribution to approximate a binomial distribution. Okay, well, step number 1 is checking those requirements again. You've already done this if you have determined that we can use a normal distribution to approximate the data, but we check this requirement again. N times P has to be greater than or equal to 5, and N times Q has to be greater than or equal to 5. Next, we want to find the population mean, or mu, and find the population standard deviation, or sigma, using these equations here, where mu is equal to N times P, and sigma is equal to the square root of N times P times Q. We need to find the population mean and the standard deviation that are going to be used in our normal distribution approximation calculations. Step number 3, identify the discrete whole number x that is relevant to the binomial probability problem that's being considered. Once we've determined what that value of x is, then we need to take into account that continuity correction. So we take this value of x and we represent that value by a region bounded by x minus 0.5 and x plus 0.5. Okay, so we don't just look at x as a value on its own, we look at x minus 0.5 to x plus 0.5. And again, we're only going to do this continuity correction if we have a binomial distribution and we want to approximate that as a normal distribution. Step number 4, graph the normal distribution and shade the desired area bounded by either x minus 0.5 or x plus 0.5 as appropriate and what's as directed in our question. Are we ready for an example of all this? Let's go through it. So for this example, was Mendel wrong? Well, in one of Mendel's famous hybridization experiments, he expected that among 580 offspring, 145 of them, or 25%, would be yellow, but he actually got 152 yellow peas. So assuming that Mendel's rate of 25% is correct, find the probability of getting 152 or more peas by random chance. In solving these binomial probability distribution problems, make sure you're comfortable identifying what is N and what is P. So try to think through those before pressing play and before looking at the answers. So N is our number of trials. Here we're told we're looking at 580 different pea plants or plant offsprings. So that's our value of N. For our value of P, we remember that's the probability of success in one of the N trials. Because we're given the success rate here of 25%, we need to take this percentage but make it into a non-percentage number. So 25% divided by 100 is 0.25. So in other words here, our N value is 580, our P value is 0.25. We want to find the probability of at least 152 yellow peas. Why is this at least 152 yellow peas? Well, because in the question we're asked to find the probability of getting 152 or more yellow peas by random chance. So 152 or more is the same thing as thinking along the lines of at least 152 yellow peas. Then we always want to talk about significance. So we're going to ask, is 152 yellow peas considered significantly high? And we'll go through again how to determine significance here. Maybe pause and try to answer this for yourself. What question are we going to ask if we're determining if something is significantly high? What does that mean about the probability? Does it mean it's less than or equal to some value of probability like 0.05? So try to pause and consider that, and then we'll talk through it. So again, here's the setup of our question. For our solution, step number 1, is our requirement check true? Can we approximate this data as a normal distribution? Well, remembering how we check those requirements, we first assigned a value of N is 580, the value of P is 0.25. We first want to check N times P. So we take 580 multiplied by 0.25, that's 145. Then remembering that P and Q are always complements, then to solve for Q, take 1 minus P, so 1 minus 0.25, that's 0.75. Then that other requirement check is N times Q. So we take 580 as our N value, multiplied by 0.75 as our Q value, we get a value of 435. Then we ask, are both N times P and N times Q greater than or equal to 5? Well, yes, right? 145 is greater than or equal to 5. and 435 is greater than or equal to 5. So both of these requirements are satisfied, both are true, then we can move on to step 2. So we've determined that we can use a normal approximation for this binomial probability distribution. So step number 2 is finding our approximate population mean and our approximate population standard deviation. To set this one up, our mean, or mu, is equal to n times p. So that's 580 multiplied by 0.25. That's 145. That should be the same value we calculated up here, and it is. Then for the standard deviation, we take sigma is equal to the square root of n times p times q. We plug in our value for n, 580, our value for p, 0.25, and our value for q, 0.75. We multiply all of these, then we take the square root. We should get a value of 10.4283. Okay, so that was step number 2. We needed a mu value or a mean value. We also needed a sigma value or a standard deviation value. So now we have those two values moving forward. Step number 3 is determining that continuity correction. So because we want to know the probability of at least 152 yellow peas, we should think of that 152 value as our x value. So for example, if we draw an approximation of a normal distribution, we'll draw this symmetric bell-shaped curve. We determined our mean and our standard deviation just on the last slide in step 2. Then we need to think about the question at hand. So we want the probability of at least 152 yellow peas. Because we know our x value is 152, then we apply the continuity correction. So to do that, we take our x value minus 0.5 and our x value plus 0.5. That is 152 minus 0.5 and 152 plus 0.5. When we do that calculation, then we represent this discrete value of 152 in our graph of a normal distribution by the interval now. So applying the continuity correction, we no longer consider just 152 as our x value. Instead, we consider this range from 151.5 to 152.5. Okay, right? And we did that by taking our x value of 152, subtract 0.5 to get the left side of the range, then added 0.5 to get the right-hand side of the range. So again, here we have 151.5, and then the range from that to 152.5. That's because our x value of interest was exactly 152. Now, step 4 is to apply the approximation of the normal distribution. So again, drawing visuals is a really good idea to do here. Keeping in mind our question, we want to know the probability of at least 152 yellow peas. Because we apply the continuity correction here for a binomial distribution in order to approximate it as a normal distribution, then when we hear 152 or more yellow peas, then we actually think of that as this normal distribution here, where we have a line at 151.5 yellow peas. So we're doing steps we've been familiar with before, but now we're applying the continuity correction. So deciding on which x value to use either in Excel or with table A2 is not as straightforward as just looking at our x value itself. Instead, we applied the continuity correction, so we got a range of 151.5 to 152.5. That range is really how we think of our x value now. Then we think of the question at hand, right? So 152 yellow peas or more. Well, I'm no longer considering just my simple x value of 152. Instead, I'm including this range now. So I really want to find the far left side, so 151.5, the lower end of the continuity correction. I want to find the probability of getting that lower end of the correction, so 151.5 peas or more. That helps us translate from a binomial probability distribution into a normal probability distribution. Okay, so really importantly, in step 3, we figured out our continuity correction, those values being 151.5 and 152.5. Now we think of our discrete x value of 152 as a continuous range now from 151.5 to 152.5. Once we've established that range, then we decide on what part of the graph do we shade. Here for this example, we're asked about 152 or more yellow peas. But that's really asking our probability value of X or more. But now we don't have a single X value, we have a range of values. So then we really think of that as 151.5 or more. And coming up in a slide, I'll go through a table talking about the different options for what does it mean for or more, at least some certain X value. So we'll go through all of that. This is going to be one of the trickiest parts in setting up a binomial distribution and approximating it as a normal distribution. But using images like this can be super helpful. So I recommend drawing a visual like this for most of the problems you'll go through in chapter 6. Okay, so at this point, we have a lot of data. Now we want to solve for our answer. One route we can go with is using Excel. So because we took binomial probability distribution data, and we want to approximate that using a normal distribution, then in Excel, we're going to use a normal distribution function that you have used before. To set up a normal distribution function in Excel, we need our X value of interest, our mean, our standard deviation, and that cumulative value. By applying the continuity correction and then deciding on which side of that range to shade, then we've decided on the X value that we need to use, so 151.5. Our mean value and our standard deviation value were calculated previously. That was in step 2. Then for our cumulative value, we know it can either be 0 or 1. Well, here we want to know the probability of all this area to the right. So we're going to use a cumulative area of 1 to get all this area to the left and then take the complement of that answer. So here's how I set up this normal distribution. Then I click enter. I get a value of 0.73345 or so. Because Excel and table A2 are always referenced as the cumulative area from the left, then we know this is my answer. That's the cumulative area from the left. We don't want this though, right? We want the cumulative area to the right of that line, where the line is at X is equal to 151.5. So to find our true answer, we take 1 minus this value is equal to 0.2665. That's our final answer. That's our cumulative area to the right of this line of 151.5. Now we can also solve this using table A2. I do recommend using Excel over A2 when you have the opportunity to do so. Because when using table A2, there's an extra step we need to do, and that is finding the z-score. So in order to use table A2, we need some z-score to go based off of. We know our X value, we determined that previously, is 151.5. We know our mean value and we know our standard deviation value. That was found in step 2. So to convert all of this into a z-score, we take z is equal to x minus mu all over sigma, or the standard deviation. Plugging in the values that we have, we get a z-score of 0.62. We had to do that first before we can use table A2. So using the table in your book, we go to a z-score of 0.62. That corresponds to a cumulative area from the left of 0.7324. Then again, because that's the cumulative area from the left, and we're interested in the cumulative area to the right, because we want to know the probability of at least 152 yellow peas, then we take the complement, or 1 minus 0.7324. We get our final answer here using table A2 of 0.2676. Now, table A2 has some approximations built into it, so using Excel, once again, is a benefit because we get a slightly more accurate answer using Excel over table A2. Now, we've done all these calculations, then the interpretation or the significance is what we'll talk about next. So to sum this up, Mendel's result of 152 yellow peas is greater than the 145 yellow peas he expected with his theory of hybrids. But we just determined the probability of 152 or more yellow peas by using a binomial probability distribution and approximating it as a normal distribution. In the steps to do so, we had to use the continuity correction to figure out our range of X values rather than using one discrete X value. When we did that using Excel in table A2, we got about 0.2665 as the probability of getting 152 or more yellow peas amongst his N number of 580 trials or 580 pea plants. Because this is our probability that we found, then we can make a statement on significance. So ultimately, we see that 152 yellow peas is not significantly high because, again, we measure significance as the probability value, and we make sure that probability value is less than or equal to 0.05 to say that that certain number of X values is significant. Well, we found this probability, we got 0.2665. That's definitely greater than 0.05. So because this probability value is greater than this probability value, then we do not have significance here. So this is a result that could easily occur with a true rate of 25%, what he expected to get for yellow peas. And remember, for significance, we're determining if something has statistical significance or if it can occur by random chance. So if P, or probability value, is less than or equal to 0.05, then we have true statistical significance. Here we do not, so we can say that the result could easily occur by random chance. In other words, we're really asking, is 26.4 that different from 25% given the data that he collected? Well, the answer here is no. Mendel getting 152 yellow peas when he expected to get 145 yellow peas. The steps we just went through to get a probability value that answers this question tells us that we do not have statistical significance, and therefore this answer that we got could occur by random chance. So in other words, this experiment does not contradict what Mendel had in mind, what his theory said. This idea of significance is a really important one here. So looking at this probability value being less than or equal to 0.05. So let me know if you have any questions about this and how we came to these conclusions. Now, so far, we've looked at a binomial probability distribution and we decided that we can approximate it as a normal distribution. In doing so, we use table A2. We also use the normal distribution function in Excel. So again, in this previous example, we used the normal distribution as an approximation to the binomial distribution. However, many technologies can be used to find the probability directly without using an approximation. And again, the approximation we used here was approximating this data as a normal distribution when really it's truly a binomial distribution. So we'll go through doing this. We'll go through it not approximating this data using a normal distribution. When we do this on the next slide using Excel, and I'll show you how to do this, the result we get is a value of 0.2650 when it's rounded. This result is more accurate than the result we got in the last couple slides in that previous example where we got 0.2665. And again, the last example we went through to get this answer was when we approximated the data as a normal distribution. So what should we do instead to get a more accurate answer? Well, we can just use Excel's binomial distribution function, and we've done this before. So let's see how we'll use Excel's binomial distribution function rather than Excel's normal distribution function. So again, to get a more accurate answer, the recommendation here is to use Excel's binomial distribution function. Using the binomial distribution function in Excel, we can calculate probability values as we've done with the normal distribution function. But here, if we have a binomial distribution, we should use this function to be more accurate. Now, in Excel, to set up a binomial distribution function, the information we need to go into this function is the number of successes, S or X, we need the number of trials, we need the probability of success, or lowercase p, and we need some cumulative value to enter. So here, importantly, we're not using a continuity correction because we're using a binomial distribution function as is. Essentially, we're treating a data set that is a binomial distribution as a binomial distribution. So check here closely what data values go into this binomial distribution function. Well, the number of successes, or X, is 151. In our question, we're asked about the probability of 152 or more pea plants Then without that continuity correction, we use this value of 151. This is really similar to an example we did in 5.2 using playoff games and finding the probability that if a team does win the coin toss and they decide who possesses the ball first, if that leads to a successful win. So again, it's tricky here to figure out, do we put in 151? Do we put in 152? Well, here we wanted the probability of 152 or more P plants. But because we work in terms of cumulative area from the left, then we use an X value of 151 to figure out the probability of 151 yellow pea plants or less. Then we take the complement to get 152 or more pea plants, which is the answer we want. The number of trials here we've established previously, that's 580. The probability of success, or the probability S here in Excel, that's 0.25, right? We were told 25% would be yellow in our problem. Then we want the cumulative area from the left, so we want that total area from the left, so we use a cumulative value of 1. When we click enter, this function calculates the probability of 151 or fewer yellow pea plants. We get a value here of 0.735. And again, in Excel, you can always set it up like this. You can also use this pop-out window to set up your function. I prefer doing it this way, but it's totally up to you. So again, so far I've used Excel's binomial distribution function, and we found an answer of 0.735 as our probability value of getting 151 or fewer yellow pea plants. But we don't want that answer. We want to know the probability of at least 152 yellow pea plants. So again, we take the complement, so 1 minus this value we get an answer of 0.265. We got this answer using Excel's binomial distribution function and plugging in the correct answer for X or S, the number of trials, the probability of a success amongst n number of trials, and the correct cumulative value. Importantly, for this particular example, we wanted to know the probability value of at least 152 yellow pea plants. We won't always have a question that asks us in this wording of at least a certain number, for example. So under the category of continuity correction, I want to talk about some other wording you might see in a question that you're asked. So again, for continuity corrections, when we're using a normal distribution as an approximation for a binomial distribution, that is, we're using a normal distribution that is a continuous probability distribution in order to approximate a binomial distribution, where a binomial distribution is a discrete distribution. So when we're treating a binomial distribution as a normal distribution, we apply this continuity correction. When we do that, we take a discrete whole number x, like 152 in our last example. We take this discrete whole number x in the binomial distribution by representing the discrete whole number x by an interval instead of one discrete value. We find that interval by taking x minus 0.5 to x plus 0.5. And again, in that previous example, we took our x value of 152. When we apply the continuity correction, we really get a range of 151.5 through 152.5. And previously, because we wanted a probability of 152 or more yellow peas, then we used the area to the right of 151.5. Keep in mind the wording we went through, 152 or more yellow peas. Here's some other ways you might be asked to apply this continuity correction. So for example, 152 or more yellow peas, that's really saying at least 152 yellow peas. That means we're including 152 and anything above that value. Then this is all after we've applied the continuity correction, then we'd really want to know the area to the right of 151.5. The next example, if we're asked to find the probability more than 152 or more than our x value, then we don't want to include 152. When we have wording like this, then instead of an x value of 151.5, we want to know the probability or the area to the right of the curve given an x value of 152.5 here. So now we're considering the upper range of our continuity correction. That is specifically when we have wording like this, so more than a certain x value. What about this wording now? So the probability of at most a certain x value. That really means we're including this x value in anything below it. So how do we apply that using table A2 or Excel? Well, we want to find the area to the left of 152.5. So the area to the left of the upper range of our continuity correction. Another example of wording, fewer than a certain x value or fewer than 152. That means we're not including 152. So to find that, we really want to take into account the area to the left of the lower range of the continuity correction or to the left of 151.5. One last example of wording you might see, so exactly 152. How do we handle that? Well, this is similar to what we've seen before. We really want to take the area between 151.5 and 152.5. So again, this is when we have a binomial distribution and we want to approximate it as a normal distribution. In doing so, we apply this continuity correction and we found the upper range of 152.5 and the lower range of 151.5. We did this by taking our x value of interest, 152, minus 0.5 and plus 0.5. Then if we're taking a binomial distribution, approximating it as a normal distribution, and we're asked about exactly 152, then to find that answer, we take the area or the probability value between 151.5 and 152.5. Let's do an example here of this last one where we're asked about exactly 152. Okay, so using the same information from the previous example, find the probability of exactly 152 yellow peas amongst the n number of trials, or 580 offspring peas. These values are the same here now. So n is 580, that's the number of trials, and p, the probability of success in one of those trials, where our definition of success here is that we get a yellow pea plant from our offspring. So that lowercase p value is 0.25. Now, instead of what we did previously, we're going to find the probability of exactly 152 yellow peas. From there, we want to answer, is this result from this calculation useful for determining whether 152 yellow peas is significantly high? Given all the different variations of the continuity correction and all the different sorts of wordings, here we're in this row. We want to know the probability of exactly X, or exactly 152 yellow pea plants. In doing so, if we're doing a normal distribution approximation, then we take the continuity correction, the bottom of that range, 151.5, through the top range of the continuity correction, or 152.5. Okay, so here's our solution. In this figure, we have a normal distribution. It's symmetric, it's bell-shaped. We also have already figured out our mean, our mu value, and our standard deviation, or our sigma value. So right now, in the middle of our normal distribution, we have our mean value of 145. Our sigma value, our standard deviation, that's 10.4283. Then also what we know is that we have an x value of 152, but given the continuity correction, we can really say that's a range from 151.5 through 152.5. Then this shaded area approximates the probability of exactly 152 yellow peas. Okay, and here's that information again. Then the region in this vertical strip of area here between 151.5 and 152.5. Now we can find the area here, the shaded area here between the lower range of the continuity correction and the upper range of the continuity correction using the same methods we used earlier. Okay, so far we've drawn this picture, we've done the continuity correction to determine this range of values for doing a normal distribution approximation of a binomial distribution. There's a few ways to solve this now, so let's go through each one. Let's go through first applying the normal distribution function in Excel. So when using Excel and we want to know the probability of exactly 152 yellow pea plants. So remember, when we're taking a binomial distribution and we're approximating it as a normal distribution, we needed to have applied those continuity corrections. So when we're thinking along the lines of exactly 152 yellow peas, then to set this up with normal distribution functions in Excel, then we need to use an X value of the lower range of the continuity correction, or 151.5, and then the upper range of the continuity correction, or 152.5. This setup should look the same other than what X value we use here. When we click enter and we get these answers here, we get 0.76399 for an X value of 152.5. When we click enter for an X value of 151.5, we should get 0.73346. Now, because we know the area to the left, which is what Excel gives us when we do these normal distribution functions, then to truly solve for this shaded region here in our figure, we want to take this cumulative area from the left minus this cumulative area from the left. In other words, we want to take the probability value from the left of 152.5 minus the probability from the left of 151.5. When we do that, we should get a probability value in that sliver, in that shaded area, of 0.03054. Again, the steps for this solution is we apply the continuity correction to binomial distribution data, then we use the normal distribution function to solve for these probability values, and then we solve for our area value by subtracting this one from this one. That was one way of doing it. We can also use Excel's binomial distribution function so we don't have to make an approximation. But you should know how to apply both of these functions to a binomial distribution kind of problem. So if we're not making an approximation, when we set this up in Excel, then we can plug in our answers and get a probability or an area value right away. But there are a few key things to note here in setting up this binomial distribution function in Excel. The important part here is we're doing exactly 152 yellow peas. So let's talk through what variables we plug in here. Our number of successes is that we have exactly 152 yellow peas. So that's our X or S value here. The number of trials did not change. The probability of successes, or lowercase p, also did not change. Now, the big difference here is that we're using a cumulative value of 0. We don't want to know the cumulative area from the left, the cumulative area from the right. We just want to know exactly 152 pea plants, or exactly 152 yellow pea plants among our N trials. So the big differences here is a cumulative value of 0, and we're using this binomial distribution function rather than the normal distribution function. When we click enter, we get an answer for this. We should get 0.0301, just slightly rounded here. Okay, so those are the differences using the normal distribution function and this binomial distribution function, both in Excel. There's one other option here. We can use table A2 if we'd like. But remember, when using table A2, we can't just use our values as is. We have to convert them to a z-score. Also remember, for table A2, this is using the concept of normal distributions. That means that we can't use an X value of 152. Instead, we needed to use the continuity correction because we're taking a binomial distribution and we're approximating it as a normal distribution. Not only that, but in order to use table A2, we have to have z-scores and we have to have treated our data as a normal distribution. So again, it's really important to keep all of this straight and to go through all these steps and really understand when to use table A2, what do we need in order to use table A2, when do we use Excel, and what function do we use in Excel. So again, in table A2, we need to treat the data like a normal distribution, and we need z-scores. So because we're doing both these things, we needed to have applied the continuity correction to get those values of 151.5 and 152.5. Then we take those X values and we convert them into z-scores. When we do so, and I showed you the equation for calculating a z-score towards the beginning of this lecture. Then when we plug in the values that we have, so our different X values, the mean and the standard deviation, we get z-scores of 0.62 and 0.7. Once we know those z-scores, then we can use table A2. When we go to table A2 and we find those z-scores and we find the cumulative area from the left for each corresponding z-score, we should get 0.7324 and 0.7642. Now again, that's basically getting this area to the left, that's to the left of the upper range of the continuity correction, and this area to the left, that's the area to the left of the lower end of the continuity correction. Once we know both of those areas, then we subtract them to get the area of interest. So the true area or the probability in this shaded region is this value minus this value, or this area minus this area, to get a final answer of 0.0318. Keep in mind what we just calculated. So this was using table A2 to find the probability of exactly 152 yellow peas. Remembering the other part of the question we were asked here, so is this result useful for determining whether 152 yellow peas is significantly high or not? To address this, let's talk about the interpretation here. So earlier, we saw that X number of successes among N number of trials is significantly high if the probability of X or more successes is unlikely with a probability of 0.05 or less. In other words, we find the probability. If that probability value is 0.05 or less, then the X value that was used to calculate the probability is considered significant. In determining whether Mendel's result of 152 yellow peas contradicts his theory that 25% of the offspring should be yellow peas, we should actually consider the probability of 152 or more yellow peas. The key point here for significance is that we're considering an X value or more. So here, our X value is 152. We want to know the probability of 152 or more when we're asked about significance specifically. So what we did in this later part of the section is we determined the probability of exactly 152 P's. That's good to know how to do, but that doesn't help us address this question of is there significance or not. So this result that we've gotten in the last part of the section of 0.0301 for that tiny sliver of shaded area, that's not the relevant probability that we're interested in. Specifically, it's not the relevant probability when we're asked about significance, where significance we need a probability of X or more. The relevant probability for this question of significance is 0.2665. That was found in the first example we went through. So generally speaking, the relevant result where we got that probability value of 0.2655, so the probability of X or more, that probability value of getting a result is at least as extreme. Now, there's a lot of different routes to go through in 6.6. Do we approximate binomial distribution as a normal distribution? And then from there, we need those continuity correction factors. And or do we use Excel's binomial distribution function as is? For all of these cases, we need to be really careful about what we call the X value. Do we apply the continuity correction or not? And which part of the graph are we shading? Is it to the left of the lower end of the continuity correction? Is it to the right of that? Or do we take the upper end of the continuity correction and shade the area to the left of that or to the right of that? Okay, so really stay organized, draw a picture, and think through these problems. This is the end of chapter 6 now, so this is all the material that will be on exam 3. Consider doing those practice exams in MyStatLab. Also consider doing a lot of practice using Excel. It can be faster, more efficient, and give you less room for errors. Let me know if you'd like to talk through any of this material. As always, call into office hours, email me, and hopefully I'll talk to you soon.